But today's video is special because we are going to learn the difference between expression, equation, and identity. And moreover, we will be proving the identities first, deriving the basic trigonometric identities that we are going to use in solving the questions. So let's wait for another few minutes so that everyone joins in, and then we can start our session. So children, as we have already done 4 streams on trigonometry, I am very sure that you must be clear with the basic concepts and the use of trigonometry. The main application streams of trigonometry, where we solve the word problems that are based on trigonometry, we are going to do it in the last, after we are done with trigonometric identities. As you know, boards are approaching and everyone is working hard to score well in board exams. So let me tell you, this trigonometric identities is very important topic, and a 4 marks question definitely comes in the exam for both CBSE and ICSE board. So I request you all to pay attention so that you understand this topic well. Okay, so before we start with identities, let's try to understand the difference between expression, equation, and identity. Though in one of my video on quadratic equation, I have explained the difference of expression and equation, but right now you can see that we are going to get introduced to a new word, identity. So it's very important to be clear that what is the difference between equation and identity. So let's do that first. And those who have joined the stream, please write hi or hello in the stream, so that in the chat, so that I get to know who all are with me. Okay, so I have switched my screen. I hope you can see my screen. Yeah. Okay, so children, when I say expression, then equation, and here is my identity. So being a math student, it's very important to understand the difference between these three things: expression, equation, and identity. So like when I say, suppose I am learning the English, let's relate it with the English language. When I am learning the words, okay, or let's say I'm learning the letters. So when I'm saying just A, B, C, these are the distinct letters. Okay, so that's kind of expression in math, which is something like if I say okay 2y, or I write y square. So these are the expressions which are just terms, okay, some random terms. These are the expressions which you don't say okay this expression is true or this expression is not true. So this true or false does not hold for the expression, because they are just terms, okay, which has constant and variable. But when I come to equation is like words made from the letters. Okay, so if I say y square equals to 4, now when the equality signs comes in this expression, it becomes equation. So you can very well see that there is a word equal in equation, okay, or equality sign. This equals to sign written in the equation differentiates it from the expression. So when I put y square equals to 4, this becomes equation. That means this equation holds true for certain variables, for some values. Now you must be wondering, then what is the difference between equation and identity? Okay, so first thing, equation holds true for certain values. It is not true for all the variables across. Okay, but identity is a type of equation. Identity has a different sign, but you might not see in the textbook, not you're taught in the school. But to differentiate mathematically between equation and an identity, what do we write? Suppose I am writing y square minus 4 and these 3 lines. Okay, So these 3 lines tells me about identity, but 2 lines that equals to sine is all about equation. But when you have 3 lines, that means it's an identity. But we don't use 3 lines while solving, or normally in the textbooks it's given by 2 lines only, or you have to identify that whether it's identity or equation. But now I come to the main point, that what is the difference between equation and identity. The equation holds true for certain values. Like here, when I solve y square equals to 4, I'll solve it for y and I'll get 2 answers. So this equation holds true for plus 2 and minus 2, right? But identity is something that is valid for all the values, that where y belongs to r, for all the real numbers. So identity is a type of equation. It is true for all the variables that are involved. So this is the difference between identity and equation. So when I write an identity, sine squared theta plus cos squared theta equals to 1, this is a very important identity of trigonometry. So what does it mean? Here I'm not writing 3 lines, I'm writing 2 lines, but it's an identity because it's like this in your textbook. So here this identity means that the theta holds true for all the values starting from 0 to 90 degree, because this is a Pythagorean identity. This is derived from Pythagoras theorem, from right angle triangle. So that's why here all the values of theta ranging from 0 to 90 holds true for this identity. Okay, so here theta doesn't have 1 or 2 values like equation has very limited solutions, right? But identity holds true for all the values. So trigonometric identity is an equation which involves trigonometric ratio of an angle. Okay, so it involves trigonometric ratio of an angle. So children, this was the main introduction. I hope you are clear with the difference in equation and identity. You can show a thumbs up in the chat if you're clear with the difference. Okay, so I'll be moving further. Those who have joined me, they can write hi in the chat. Thank you, Rohan, for acknowledging. Yeah. So now let's prove the identities. Okay, so this is the first identity, sine square theta plus cos square theta equals to 1. You have one more identity, that is 1 plus tan square theta is equals to secant square theta, and then you have 1 plus cot square theta equals to cosecant square theta. So children, learn these identities, but many few know how it is derived and why it is like that. So it's very simple and it is directly proved from Pythagoras theorem. So we can do it in few minutes. Okay, so just look at the proof, you will understand it very well. Okay, so I'm going to draw one right angle triangle. Okay, so here is my right angle. Okay, now if you look here, I have this angle theta. Okay, and my triangle is right angled at B. Now when I write the Pythagoras theorem, I write it like AC square equals to AB square plus BC square. Everybody is aware of this, right? What happens when I divide the entire equation with AC square? Okay, it doesn't make any difference if I am dividing with AC square on both the sides, right? So AB by AC square, so I can write it like this, and this also can be written like this. Okay, so AC square upon AC square is 1. And what is AB by AC? You can clearly see that AB by AC is perpendicular upon hypotenuse. Correct? So what is my perpendicular upon hypotenuse? That is sine square theta. So I can write here sine square theta. And what is BC upon AC? BC is my base. AC is my hypotenuse. Correct? So base upon hypotenuse gives me cos theta. So I can write here cos square theta, and here goes my first identity, right? So this is what I have proved from Pythagoras theorem. Now if I divide this same equation, AC square equals to AB square plus BC square by AB square on both the sides, so I can write it something like this: AC by AB whole square equals to AB square by AB square and plus BC by AB whole square. Okay, so here now second step, first I took hypotenuse and I divided the entire equation by hypotenuse and I got this first identity. This identity holds true for all the values of theta ranging from 0 to 90 degree. Okay, now when I took AB, AB is my perpendicular, so I am dividing the entire equation with perpendicular. So AC by AB gives me, AC is my hypotenuse and AB is my perpendicular. So we know our Pandit ji wala formula, Pandit Badri Prasad har har bhole sona chandi tole, right? So now AC by AB, AC by AB is hypotenuse upon perpendicular. So what is the reciprocal ratio of sine? It is cosecant, right? So I can write cosecant square theta, AB square get cancelled 1, and BC by AB. BC by AB is base upon perpendicular. So which is the reciprocal ratio of tan. So I can write cot square theta because reciprocal of tan gives me cot theta. So 1 plus cot square theta gives me cosecant square theta. So I have proved my second identity also, right? Now which side is left that I have not used so far? So I have not divided the entire equation with BC. So let's do that now. So here AC by BC whole square equals to AB by BC whole square plus BC by BC whole square. So here it is when I am dividing the entire equation by BC. So now what is AC by BC? AC is my hypotenuse and BC is my base. So hypotenuse upon base is the reciprocal of cos, that is secant. So I can write here secant square theta. And what is AB by BC? AB by BC is perpendicular upon base. And what is perpendicular upon base? That is my tan square theta, right? Tan theta. So I can write here tan square theta and this BC get cancelled. So 1. So 1 plus tan square theta is equals to secant square theta. So I have proved all the three identities, right? Okay, so this is how you prove the identities and we have learned the difference between expression, equation and identity. I hope you are clear with this much. So now further we are going to solve 6 identities, 6 questions, proving questions based on trigonometric identities. So I'll be back after a short break. Okay, so hello Miss Archana, welcome to Deep Tips. Okay children, so here we have first question which says cosecant A minus sine A into secant A minus cos A into tan A plus cot A equals to 1. So we have to prove this question. So in this kind of question, first I want you to understand how to approach the trigonometric identities, how to approach the proofs, because there are certain ways where you sometimes get stuck in the proof. So I don't want you to get stuck. So see children, there are 2-3 ways in which you approach the problem. First, when you look at the question, you look at left hand side and right hand side. So this is my left hand side and this is my right hand side. So which one is simpler? Right hand side looks pretty simple because it is just 1. You have to prove that left hand side equals to right hand side. Left hand side is a huge expression and right hand side is 1. So how do we do that? So whenever you have a difficult left hand side and the pretty simple right hand side, you start with the messy one, the one which is giving you stress, lots of stress. Take that side, left hand side, and simplify it so that you reach right hand side. So let's begin. So I'm writing here LHS. How you do this in the question, you write left hand side and then you copy down it. So I'm writing here cosecant A minus sine A into secant A minus cos A into tan A plus cot A. So I have written my left hand side here. Now right hand side is not giving me any clue that I need tan, cot, whatever. I just need 1 on the right hand side. So how do I get that 1? Either everything get cancelled and 1 is left, or I get some fractions where numerator and denominator get cancelled, then I can get 1, right? Or somehow I should reach the final identity as cos square theta plus sine square theta, which is equals to 1. So I have different ways to reach there, but I need to find out which one is the correct. Okay, so here I can see that I have few reciprocal ratios also, like cosecant, secant and cot. I have the reciprocal ratios. So what I can do, I can just simplify these ratios in the, like cosecant A can be written as 1 by sine A. Okay, so I have simplified my first bracket a bit, not fully but a bit. Secant A I can write as 1 by cos A and minus cos A. And here tan A, now you can see that in first 2 brackets I have everything in sine and cos, and there is the possibility of changing tan and cot to sine and cos form, right? So I should go with that because it's looking bit simple now, right? So tan A can be written as sine A upon cos A, and cot A can be written as cos A upon sine A. Okay, so everybody is clear with that? Yeah. So now if you look here, now I know 1 by sine A minus sine A. So I have a fraction here. If I take the LCM sine A, I get here 1 minus sine square A. Yes. Now if I take again LCM here, I get cos A, and this is 1 minus cos square A by simplifying the fractions. And in the last bracket, I have my LCM as cos A and sine A. And when I simplify, I am getting something desirable now. Sine square A plus cos square A. Correct? Now, if you look here, 1 minus sine square A is equals to cos square A. From the identity that we have done, we know that cos square A plus sine square A is equals to 1, right? If I take sine square A on the other side, I can write 1 minus sine square A equals to cos square A. So I can use that result here, right? So this is cos square A upon sine A into, now 1 minus cos square A is sine square A. Sine square A upon cos A. Now this is sine square A plus cos square A, which is 1 upon cos A into sine A. And in the exams, it is very important to write the identities used. So if you are writing sine square A plus cos square A equals to 1, so it is important to write it. If you are writing that sine square A equals to 1 minus cos square A, you are using these. So you just write all these. Okay. So now children, if you look here, I can cancel all these because sine A into sine A, this sine A into sine A gives me sine square A. So let's cancel these sine square A. Now cos square A, cos A into cos A. So what I am left with? I am just left with 1, which is my RHS. So I can write LHS is equals to RHS. Okay, so this is how we solve the identity. Okay, so this is how we solve the identity, and where we do LHS equals to RHS. So that's what I was saying. Whenever you have this kind of question, first try to analyze what's in left hand side and what's in right hand side, then try to simplify it. If there are reciprocals and you need the original ratios, just do it and do the normal calculation. And in grade 10 you have only 3 identities to do with, so those identities we have proved in the beginning, and actually you can derive 3-4 more identities from there, like what we did here. We know cos square A plus sin square A equals to 1, so we can write 1 minus sin square A equals to cos square A, and we can write 1 minus cos square A equals to sin square A. Same way we can do for 1 plus tan square theta equals to secant square theta, then 1 plus cot square theta equals to cosecant square theta. So here also we can just manipulate these trigonometric identities and we can use those in our questions. So I hope you are clear with the question 1. So I'll be back after a break for second question. Yeah, so okay, so my second question is, if 7 sine square theta plus 3 cos square theta equals to 4. In the previous question we had something in LHS and we had to prove in RHS that it is equal to 1, but now one condition is given, that 7 sine square theta plus 3 cos square theta is equals to 4, and we have to show something. Then show that tan theta is equals to 1 by root 3. So this is the question, that a condition is given and we have to show that tan theta is 1 by root 3. So how to go about it? If anybody knows the answer, you can type in the chat. Okay, hey, hi Umang, great to see you in live stream. Thank you so much for tuning in. Okay, this is simple trigonometry, Umang. I hope you will be able to understand. Okay, so what is given? 7 sine square theta plus 3 cos square theta equals to 4, and we have to show that tan theta is 1 by root 3. But there is one more condition, that we don't have to use any trigonometric table, right? Okay, so this is something that we need to prove, but how? So I know one trigonometric identity here, that sine square theta plus cos square theta equals to 1, right? But here the thing is, I have 7 sine square thetas and 3 cos square thetas. So how do I make sine square theta and cos square theta 1? So what I can do, I can write 7 as 3 plus 4, because I know I want 3 sine square thetas to club 3 sine square theta and 3 cos square theta. So let's split it. So I can write 4 sine square theta plus 3 sine square theta plus 3 cos square theta equals to 4. Okay, now if you can look here, this 3 sine square theta and 3 cos square theta, I can club them together. Okay, so 4 sine square theta stays like this, and we are going to take 3 common here. So sine square theta plus cos square theta, which is equals to 4. Okay, so now sine square theta plus cos square theta is 1. So 3 into 1 gives me 3 only. And this 4 sine square theta can be taken to other side because I have 4 there, right? So 3 equals to 4 minus 4 sine square theta. Okay, so now 3 equals to 4 into 1 minus sine square theta, and we know that 1 minus sine square theta is cos square theta. So which implies 3 equals to 4 cos square theta. You must be wondering what I am doing here. So children, this was a different question from the previous one. Here there was no LHS and RHS to prove like directly, but a condition is given. So first we need to take out something from that condition that is similar to the thing that we have to show. Okay, so I could clearly see that the condition that is given, it has sine square theta and cos square theta, but not directly. So I need to break that 7 in two parts, 3 sine square theta and 4 sine square theta, so that I can club 2 and I can take 1 4 sine square theta on the other side, so that I get some cos square theta. But I am still not done, because cos square theta does not solve the purpose of getting tan theta. Now I have to do more brainstorming, that how do I get tan theta when I have cos square theta. Okay, so now think of some more trigonometric ratios. Let's do it further. So cos square theta is equals to 3 by 4. But I am nowhere getting tan theta from my cos square theta. But we have done one trigonometric ratio in the beginning, and that was based on 1 plus tan square theta equals to secant square theta. And I know that the reciprocal of cos square theta gives me secant square theta, right? So if I do the reciprocal, I can write secant square theta equals to 4 by 3. Does that make sense? Yeah, now you got to know that why I was doing all this. So now when I am having secant square theta, I can replace it with 1 plus tan square theta, which is equals to 4 by 3. Now the question says find the value of tan theta. I can simplify it further. Yes, so tan square theta is equals to 4 by 3 minus 1. And tan square theta equals to 4 minus 3 by 3, which is equals to 1 by 3. And when I just take the square root on both sides, I get tan theta equals to 1 by root 3, and hence it is proved. Isn't it interesting? We started from some sine square theta and cos square theta, and how eventually we landed on tan theta. So you need to keep all your things in the mind, all the trigonometric identities in mind to solve it. And keep all your options open, because there are many ways to solve a trigonometric identity. Okay, so I hope you are clear with this. Now third question that we are going to solve is different from the first two. Okay, so sine theta upon 1 minus cos theta is equals to cosecant theta plus cot theta. Okay, the question says sine theta upon 1 minus cos theta is equals to cosecant theta plus cot theta. Now in the exam, when this kind of question comes, children often get stressed out. Now what to do? So don't panic. First thing in the exam, never panic after seeing the question. Calm your mind, gather your thoughts, and then apply the learning. This is the mantra to do well in math exam, that never panic after seeing the question. You just need to gather all your thoughts, relax your mind, and then solve step by step. So here when you see this kind of question, I can very well see that I have sine theta in the numerator and 1 minus cos theta in the denominator, right? And in the RHS I have cosecant theta plus cot theta, which are looking pretty relaxed and simplified, right? So this left hand side is looking little messy. So why not to start with this and simplify it to make it RHS, right? So now how do we do that? So if you look at this, I can relate it very well with the surds. You know surds, doing the rationalizing. Okay, so here why I need to do something, because to get cosecant theta and cot theta, for cosecant theta I need 1 by sine theta, and for cot theta I need cos theta by sine theta. To reach RHS, if I simplify this RHS, I need 1 by sine theta plus cos theta by sine theta. correct? But here I have sine theta in the numerator and 1 minus cos theta in the denominator. So if I take my LHS, okay, if I take my LHS, I get sine theta upon 1 minus cos theta. How do I reach this? This is the problem. This is the main problem, that how do I get sine theta in the denominator? So I know if I rationalize this, means multiply and divide with the same expression, it doesn't change my LHS, correct? So what do I do? If I multiply 1 minus cos theta with 1 plus cos theta, what do I get? I get 1 minus cos square theta, which is very well equal to sine square theta. So this solves my problem, correct? So now if I do 1 plus cos theta upon 1 plus cos theta, this does not harm my LHS at all. My left hand side remains the same because indirectly I am multiplying it with 1. So any number multiplying by 1 gives you the same answer. So same here, sine theta upon 1 minus cos theta is being multiplied with 1 plus cos theta upon 1 plus cos theta, correct? So it should not do any changes to my original expression. So now in the next step I can continue solving. So what would I do now? Sine theta into 1 plus cos theta upon 1 minus cos square theta, because I know that a plus b into a minus b gives me a square minus b square. A plus b into a minus b gives me a square minus b square. So that's what I have done here. But we know that 1 minus cos square theta is equals to sine square theta. So let's simplify this. Sine theta into 1 plus cos theta upon sine square theta, right? So this get cancelled and I am just left with 1 plus cos theta upon sine theta, which is still not my RHS, but I am very close to it, because if now I can rewrite this expression as 1 upon sine theta plus cos theta upon sine theta, correct? I can write this 1 upon sine theta plus cos theta by sine theta. So this is the reason why I started multiplying and dividing with the same number and then solved, because here at this step I can't write sine theta upon 1 minus sine theta upon cos theta. That is completely wrong. So that mistake you should never make in the exam. You cannot write it as sine theta minus sine theta by cos theta. This is completely wrong. Okay, so that's why to simplify it and to make it equals to RHS, I needed a single term in the denominator. So I got 1 plus cos theta upon sine theta, which I can now write as 1 by sine theta plus cos theta by sine theta. Now if I solve it further, 1 by sine theta gives me cosecant theta, and cos theta by sine theta is equals to cot theta, which is my RHS. So I can very well write now LHS equals to RHS, and hence proved. So this is how we solve this question. I hope you are clear with the concept. If you have any doubt, please type it in the chat. And I'll be back after a short break. Yes, so here is my fourth question, and it has a 6, it's raised power 6. So yeah, this is also sometimes becomes a problem in the exam when you see such huge powers and you really get confused. So here secant theta raised power 6, okay, secant raised power 6, okay, and tan theta also raised power 6 plus 3 tan square theta secant square theta plus 1. So this is something you need to solve. But here the thing is, it's very difficult to identify, because left hand side looks simplified, kind of simplified, actually it is not, and right hand side looks quite messy, quite complicated. So sometimes children start solving from the RHS to reach LHS, but I don't know, like that becomes little more complicated in the exam, because secant theta to tan theta, there is one simple identity that can be used. So what kind of approach we shall use for these kind of questions? So for these kind of questions, we can like take our LHS, where it is secant 6 theta, and which secant raised per 6 theta, and which looks pretty simple, but actually it is not, because we know the formula for secant square theta, and which can be simplified further to tan theta. So if I start thinking that way, that how secant can be changed to tan theta, and then I keep on solving further, and I know I can do the cube also, and I know the formula for cube, and I will reach tan theta eventually, then it becomes easier. So just look at the way how I do this. So I know that this can be written as secant square theta raised power 3. Correct? So children, why I wrote like this, why I didn't write 3 inside and 2 outside? You might be wondering that we know the formula for square also, but my identity holds true for secant square theta, that is 1 plus tan square theta. That's why I chose to keep secant square theta inside the bracket, and I kept it like whole cube. Okay, so now if I simplify this, this can be written as 1 plus tan square theta whole cube. Correct? Now see, things are looking pretty simplified now, because I know the formula for a plus b whole cube, and we know that a plus b whole cube is a cube plus b cube plus 3a square b, or 3ab into a plus b. I prefer to write 3ab into a plus b because I'm used to it from my childhood. Okay, so we can solve it further also, 1 as it is, and we know that tan square theta whole cube gives me tan raised per 6 theta, and I very well got 2 terms from my RHS by doing this. And now if you look here, last term is 3 tan square theta into 1 plus tan square theta, and the term that is missing in my this simplification is this 3 tan square theta into secant square theta. So here the tip is, first look at your RHS, that what you are actually going to prove. So I know that I need this secant square theta, and 1 plus tan square theta is very well equal to secant square theta. So I shall not open the brackets here. I should stop here by just substituting 1 plus tan square theta equals to secant square theta. I should not open the brackets, because if I open the brackets, I get 3 tan square theta plus 3 tan raised by 4 theta, so which is not giving me RHS. So to get the RHS, I will stop here. I will just take a pause, look at my question, recall the identities, and then substitute. Okay. So I'll write here 3 tan square theta into secant square theta, and which is equals to my RHS. So I can write LHS equals to RHS, and hence proved. So this is how you solve the questions which has huge powers. Okay, so now we are going to do our 5th question, a very interesting one. Okay, so that is secant square theta minus sine square theta minus 2 sine raised by 4 theta upon 2 cos raised by 4 theta minus cos square theta equals to 1. So this is the question. This is something that you have to prove. Okay, so how to do this? So first thing, LHS is complicated and RHS is simplified, right? Like how we did in the first question. So we will start with LHS, and here when I am saying we'll start with LHS and we have to reach the RHS, which is equals to 1. So I have few options. Either I should get sine square theta plus cos square theta in the end, or something in the numerator and denominator should be same. Third thing, everything should get cancelled with leaving with something like 1 plus, okay, sine square theta plus cos square theta or something like that, which is equals to 1. So these are the 3-4 possibilities that are applicable in this kind of question where RHS is 1. So how do we go about it? Now I can very well see that I have only one reciprocal ratio here, that is secant square theta. Sorry, rest all are in sine square theta and cos square theta, and some powers are sine raised per 4 and cos raised per 4. So I can take that common from here, right? So let's write it as secant square theta minus, here I can take sine square theta common, so that in the brackets I am left with 1 minus 2 sine square theta. In the denominator I can take cos square theta common, so that in the brackets I am left with 2 cos square theta minus 1. Okay, so this is what. Now children, again I'm still confused now what to do. It's still not giving me any clue that how to go about it. Either shall I write sine square theta by cos square theta as tan square theta or do something, or what else? So this is the problem that we face, because this is a 4 marks question. Okay, so here I can visualize something, that one is sine square theta plus cos square theta, correct? And if I substitute sine square theta plus cos square theta in place of this 1, I might get something in the numerator and denominator. So let's do it and see how it works. So secant square theta as it is, and here I am writing sine square theta as it is, sine square theta plus cos square theta minus 2 sine square theta, right? And here I have cos square theta as it is. Now 2 cos square theta, so here it is minus 1. So my sine square theta and cos square theta will change their signs, because when I open the bracket, signs changes. Okay, so now if you see here, let's solve it further. Sine square theta into, now sine square theta minus 2 sine square theta gives me negative sine square theta. So I can write here cos square theta minus sine square theta. Okay, and in the denominator I have cos square theta, and if I solve it, 2 cos square theta minus cos square theta, I get cos square theta minus sine square theta, and things are working out well for me, right? And this get cancelled, and I am left with secant square theta minus sine square theta. Just a minute. Okay, sine square theta upon cos square theta, correct? But now there are two ways to do it. Either I change sine square theta by cos square theta to tan square theta, so I can write secant square theta minus tan square theta, because I know that 1 plus tan square theta is equals to secant square theta, right? So 1 is equals to secant square theta minus tan square theta. So this is equals to 1, and I can write LHS equals to RHS. But somehow, if you don't remember the identity here, there is another way to solve this. You can change this secant square theta to 1 upon cos square theta, okay, minus sine square theta by cos square theta, taking cos square theta in the denominator and 1 minus sine square theta on the top. If you solve it further, you get cos square theta by cos square theta, which is also equals to 1. So both the ways are correct. Okay, So this is how we solve this kind of problem. So here RHS was 1. So but if RHS is not 1, it is secant square theta minus tan square theta, then definitely you will get your answer here. Or you can solve it this way also. So both the methods are correct. So this is how we solve this kind of question. So I am left with one more question, which is a very important question and 4 marker. So that we'll do after a short break. Okay, so I hope children you are clear with the concepts that we are doing. We have done 5 trigonometric identities so far. If you are clear, you can post you can write or send a thumbs up in the chat. If you have any doubt, you can post your queries in the chat. I'll be happy to answer those. So yeah, you can write in the chat so that I get to know who all are connected with me. Okay, so question number 6 is a special kind, because so far the questions we did was left hand side and right hand side. From these two sides, one was complicated and one was simplified. So what did we do? We started with the complicated one and we make it simplified, like what is on RHS. Okay, sometimes both sides look simplified, both look simple, so we take one and then we solve it. Now this is the third one. Sometimes a question comes in the exam in which both the sides look so stressed out kind of thing, so complicated, that we also get confused now where to start with. Which one is complicated? Actually I am finding both are complicated. So now in the 6th question I'll tell you the trick to handle those kind of questions. Okay, so here is the question which says tan A plus cosecant B whole square minus cot B minus secant A whole square equals to 2 tan A cot B into cosecant A plus secant B. Pretty interesting, right? Both the sides are equally, wow, what should I say? Yeah, so like children really get confused. No, shall I do inky pinky ponky, or what should I do, and which side I shall choose to start with? So children, to do such kind of question, like this kind of question, there is a trick. First I'll tell you the trick and then we'll solve the question. Okay, so first you start with LHS and you write step 1 2 3 4 5. Suppose in 6th step you might reach somewhere like tan theta, which is very simplified, and you just take a deep breath. Okay, I have reached somewhere which is simplified and so happy. Yeah, so but right hand side is also equally stressing you out. Now what to do? So you do start your RHS, you write step 1 2 3, and suppose in step 4 you reach tan theta. Oh, what a pleasure, what is a like relief, correct? But what are we doing here? We reached tan theta, in both, but question is asking something else. Question is asking prove LHS equals to RHS, but you are proving LHS and RHS equals to tan theta, but you are actually giving yourself the answer to solve this kind of query. How? See, you reached tan theta here and you reached tan theta here also. And if you start doing the reverse engineering here, reverse these 3 steps, then of course you will get to RHS. If you write this step 3 2 1 here, then you will be reaching your RHS. Yeah, you got me? So this is the trick to handle such kind of question. So You start with LHS, you start with RHS, you reach the common point, and then you do the reverse engineering, reverse mathematics here, and do the trick and reach the RHS. So this is the mantra to solve such kind of complicated questions. So now let's start with this question in the same way so that you understand what I mean to say clearly and completely. Okay, so just give me a moment. Fine. Yeah. So I will be drawing a line in between, because one side I'm going to solve LHS and other side I'll be solving the RHS. So here is my LHS. Okay. So what we shall do? We shall first write the LHS as it is down. So I'll be using two colors here. Okay. So tan A plus cosecant B whole square minus cot B minus secant A whole square. Yeah. So children, this is my LHS. So if I want to solve this, there is whole square in both the brackets. So I know the formula for A plus B whole square. So let's apply that. So we will write tan square A plus cosecant square B plus 2 tan A cosecant B. Okay, so this is my formula for A plus B whole square. Now let's write the formula for A minus B whole square. So this is cot square B plus secant square A minus 2 cot B and secant A. Okay, see, this is pretty big. I'm just moving out of my place, out of my LHS, doesn't matter. Okay, this is my simplification of the formula. Now how to do it further? Let's open the brackets. So I get tan square A plus cosecant square B plus 2 tan A cosecant B minus cot square B minus secant square A plus 2 cot B secant A. Oh, yeah. So we are done with the formulas, right? We have opened the brackets, we have changed the signs wherever required. Now what is next? So the next step is to find the pairs, to find where we can use the identities. So children, we know that 1 plus tan square theta is equals to secant square theta. So if I get tan square theta minus secant square theta, that will be equals to minus 1. Okay, right? Same way, if I write 1 plus cot square theta equals to cosecant square theta, and if I am getting somewhere cosecant square theta minus cot square theta, it will be equals to 1. So I'm going to use these identities. Why I wrote this? Because I can see somewhere these kind of pairs. Yeah, if you look here, this is tan square A and this is secant square A. So tan square A minus secant square A gives me minus 1. So if I write them together, okay, let's first pair them so that you find it easy to understand. I can write here tan square A minus secant square A. Okay, now you can see cosecant square B minus cot square B. So let's club them. Cosecant square B minus cot square B. Okay. Now I am left with 2 tan A cosecant B and 2 cot B secant A. I can't do anything much with them, but first let's write them. 2 tan A cosecant B plus 2 cot B secant A. Correct? Now let's substitute. I'm putting my equals to. Yeah. So here minus 1 plus 1 plus 2 common. Now I know tan A can be written as sine A by cos A. Okay. And cosecant B can be written as 1 by sine B. plus cot B can be written as cos B by sin B, and secant A can be written as 1 by cos A. Now these ones get cancelled, minus 1 plus 1, but I can see here something good happened, that cos A sin B cos A are same. So I can take them as my denominator, cos A sin B, and in the top I can write sin A plus cos B. So I have reached somewhere, but I don't know, I am still lost, because this is not something that I desired for, because my RHS is completely different and I have reached somewhere to sin A plus cos B upon cos A sin B. But don't worry, as I told you, these types of questions are supposed to be handled in a different way. So now let's begin our journey in RHS. Let's see what can be done in RHS. Do we get somewhere close to what we got here? Okay, so here I have my RHS, so I can write 2 sin A upon cos A. So this expression I am solving due to shortage of space. I am just solving it directly. 2 sin A upon cos A, and cot B can be written as cos B upon sin B. Okay, and this cosecant A can be written as 1 by sin A plus 1 by cos B. Okay, so 2 now sin A cos B, let's club them together, cos A sin B. You can very well see that I cannot do anything with my sin A cos B cos A sin B. This is just an expression here. But here what do I have? I have 1 sin A plus 1 cos B. If I take this sin A cos B upon cos A sin B inside, then there are chances of cancelling something. Correct? So let's write this 1 by sin A plus 1 by cos B as it is. Okay, now in the next step I am keeping my 2 out, but I am taking this inside. Sin A cos B upon cos A sin B sin A. I am multiplying both the terms inside the brackets with this term outside. Okay, so I am writing here sin A cos B upon cos A sin B cos B. Cos B cancelled, sin A cancelled. So what do I get here? I get here 2 cos B upon cos A sin B plus sin A upon cos A sin B. Now let's see if I am close to my LHS. And yes, I am exactly getting the same thing what I got on my LHS. Just a minute. Oh, what a great sense of accomplishment, that after doing such a hard work, such a long calculation, I am getting cos B plus sin A cos B plus sin A upon cos A sin B and cos A sin B on my RHS. So here that means I need to write these 3 steps in reverse and I get what is there on RHS, right? So if I start just copying down these steps further here, so what it means to say, it is just saying that you should rearrange cos B and sin A and write here cos B upon cos A sin B plus sin A upon cos A sin B. Yeah. Now next step. What is the next step that I should write? I should copy this step now. That says multiply sin A with cos B term and cos B in the second term. So let's do that. So cos B into sin A upon cos A sin B sin A plus here what I have to do, sin A cos A sin B cos B. Yes. Now what next? Take away sine A cos B common, because I can take sine A cos B common. So let's write here 2 sine A cos B common, and cos A sine B, cos A sine B, cos A sine B also, cos A sine B. So what's left? 1 upon sine A plus 1 upon cos B. Correct? So now I know that sine A upon cos A is tan A, cos B upon sine B is cot B, 1 upon sine A is cosecant A, and 1 upon cos B is secant B, and that is my RHS. So LHS equals to RHS, hence proved using the reverse mathematics, reverse engineering of RHS. So this is the huge question that you have to do, but all these steps you got from the reverse engineering of RHS. So this is how you tackle with this kind of question. I specifically used or found this question to explain you in this live stream, because if I just tell you okay, just do LHS, get to a common point and then take RHS, you might not understand. But I'm sure with this example, with this question, you will definitely understand that how I used my RHS to prove LHS equals to RHS in the end when I was at a common point. So after this common point, what I did here reverse steps trick. Okay, so children, I hope you are clear with the concept. I am done with trigonometric ratios, questions and answers, and proving the identities. And more importantly, we learned two important ways to solve that. If LHS and RHS, one is simplified, one is tricky, start with the tricky one and make it simplified. If both are tricky, start with both, reach to common point and then take RHS and do the reverse steps. Okay, and if the both look simplified, just take the fractional one and do the multiply or divide with the same number and then solve it further. So these three methods are taught in this trigonometric identities using different questions, because I feel just only telling you the methods, okay, do this, do that, might not work, because sometimes children understand better with when they are given a certain example. So that's why I tried my best to pick out the sums which are unique and different and came in board exams. That's important. So questions that came in board, I chose those questions and solved with you so that you understood the concept, understand it properly. And also in the beginning we worked on the foundation where we try to understand the difference between expression, equation and identity. So this is all we did in this 1 hour, and I am sure if you go through this live stream fully from beginning to the end, you will be very much clear with the identities and the questions based on that, and you will not lose the 4 marks in the exam. So stay tuned with Deep Tips for better learning and the things that you don't get in your classroom but you do get in the live stream with me. So I'll be back with more fun facts and the new things about trigonometry that you are not aware of. So keep watching Deep Tips. Share my channel with your friends. Subscribe to it for more notifications. Thank you so much for tuning in.